Hi, my name is Daniel Farias, and now I'll present the topic of my article Topology and Lattice Optimization, a design of wing-fuselage attachment component for an Aerodesign aircraft. The article was written by me and Professor Dr. Guilherme Ribeiro Beni from Universidade Federal da Bahia. This presentation will be divided into 5 main topics, beginning with the introduction, followed by the theoretical concepts, case study, results evaluation, and finally the conclusion. Well, the aeronautical industry is characterized as one of the most dynamic society's economic sectors. Through it, one of humanity's greatest technological leaps was provided, accelerating social relations in all areas. Facing a constant need to renew itself, associated with the need to reduce weight, the aeronautical industry has always sought solutions to increase the efficiency of its projects. Meanwhile, in the academic world, projects like the Aerodesign Formula SAE and Baja encourage students to think about innovative solutions, inserting them in a highly competitive and educating environment. Such projects enable students to develop important knowledge related to the mobility industry. In this context, especially Aerodesign faces a major challenge related with optimizing the weight of radio-controlled aircraft developed by students. In order to obtain a competitive aircraft, load studies, material selection, and structural optimizations must be developed. Such projects enable students to develop important knowledge related to the mobility industry. Here you can see the aircraft designed by the Asha Fly team, where on the table to your right, you can see the score obtained by reducing the weight of each of these items separately, and also the total score. Well, as a general rule, an optimization can be divided into 3 main concepts, which are the design variable, the cost function, and the constraints to the optimization problem. The first topic, which we'll pass through, is the topology optimization. A topology optimization begins by a discretization of an initial domain, and also by the setting of the boundary conditions and the load cases to the part. After that, the optimization software will then elect which of the discretized elements will be necessary for the final design after the given conditions. This result is then interpreted and then verified and finally manufactured. In other terms, topology optimization begins by the finite element model settings, followed by the design space and boundary condition settings, which are all given by the user. And finally, the optimization itself begins. This optimization has 2 parts. The first one is the user input parts, which will be the definition of the objective of the optimization and also the restrictions of the optimization. The other part is then given by the solver, which means the computer making the optimizations. The solver will realize the finite element analysis, followed by a sensibility analysis to understand which of the areas of the part are more sensible to the changes and to the loads that are being applied to the part. After that, a response filter is also applied, and finally a model update is made. If the model hasn't converged, the process begins all over again from the finite element analysis, and it goes through until it converges. After the conversion, the post-processing is made, and finally we can achieve the results. On the right, we can see a topology optimized part. It's a brake caliper from Bugatti, and the topology optimization was coupled with a thermal analysis to achieve this result. The second topic approach on this presentation are the lattice structures. According to McConaughey, lattice structures can be defined as topology-ordered, 3-dimensional open cell structures with strut elements connecting the cells through cell nodes, usually repeated in a specific pattern, allowed to be manufactured normally through additive manufacturing. Here we can see 2 examples of cellular materials. The first one is the already mentioned lattice, and the second one is the metallic foam. On these 2 graphics, beginning with the letter A, we can correlate the kind of application of different cell structures with a type of porosity. coming from highly functional and open cell structures, which can be used as heat exchangers, from structural cell materials, which are usually closed, that can be used as load-bearing components and energy absorbers. On the graphic B, we can see the distribution between these different cellular materials coming from a periodic or stochastic type of pattern repetition, and also from an open cell or closed cell type of cellular material. We can see the lattice structures are usually characterized as open cell periodic materials. There are multiple types of lattice structures, and beginning with one of the most commons, which are the cubic with a body centered, and its variation is Z, and also a cubic with face centered, and its variation is Z, and also a cubic and octatruss, and also Schwarz diamond. Lattice structures characteristics are mainly influenced by material, cell shape, and relative density, composed by the density of the part over the density of the material. The material influences the solid properties, which are the mechanical, thermal, and electric properties. The cell shape, they mainly influence the behavior of the structure while being loaded, and this is usually obeyed by Maxwell's criteria. And the structures can be divided into bending or stretch-dominated structures. And finally, the relative density, which is influenced by the truss length and the diameter of the trusses. After these three models are superposed, we finally have the lattice properties. The stress and strain graphics for the two type of structures we are approaching, which are bending dominated and stretch dominated lattice structures, can be seen on the two graphics. It's possible to notice that the stretch dominated structures are usually more indicated for applications which are under higher values of tension, while the bending dominated structures are usually more indicated for applications that require a higher absorbed energy, since on this case we don't have this post-use softening that occurs on the stretch dominated structures. The case study for this article was an attachment part of an Aerodesign aircraft that couples the wing with the fuselage. The material utilized for the study was a resin. The failure criteria considered was von Mises, and here you can see some of the characteristics of this material. The attachments C1 and C2 are locked in all degree of freedoms, while in C3 there is a lock only in the translational Z to represent the fixation between the attachment and the tube section wing spar that passes through the whole wing. The loads were applied on the hole where the wing spar passes through, and they were considered to be the bending moment, the torsion moment, and also the lift, caused by half of the wing. The software utilized to make this optimization was the Altair Inspire. On this slide, it's possible to see the load distribution across the wingspan for the shear stress, the bending moment, and the torsion moment. It's important to notice that the loads were applied on the root of the wing, where they find their maximum values. The first result obtained was from a non-optimized model. Both the displacement and the von Mises stress were analyzed, as well as the natural frequencies from the first 6 modes. Here you can see the full mass, as well as the maximum displacement obtained, and also the maximum von Mises stress. The safety factor obtained for this result was 1.8. The second result obtained was from a topology optimized part. Here you can see the result, and also the displacement and von Mises stress. By analyzing this result, it was noticeable that there was a decrease on the mass of almost 30%, followed by an increase on the maximal displacement of almost 180%. However, the influence of this maximal displacement increase was not considered for the final result of the part, since to really understand this influence, it would be necessary to realize a coupled analysis with the aerodynamic model and the structural model. Followed by that, there was also an increase of the von Mises stresses and consequently a decrease of the safety factor of the part, with the final safety factor of 1.6. Another interesting factor to be observed is a change on the natural frequencies of each of the 6 first modes of the part, with a decrease on the 4 first modes and up from the 5th, a small increase. This slide contains the illustration of each of the 6 modes for a non-optimized and a topological optimized part, as well as the graphic with a comparison between all of the 6 modes for both parts. It's important to say that on the 4th and on the 6th mode, the way that the pieces were behaving were the same. However, on this photo, they don't appear to be on the same position, even though they were behaving on the same way. The third and final design was the one of the lattice optimization, where the software positioned and dimensioned the lattice trusses across the design space. It's interesting to notice that there was a decrease of the mass once again, but in this time of 31%, and a maximum displacement increase of almost 670%. However, this value was once again not considered for the same reason as of the previous one. Another interesting number was the one of the von Mises stress, where there was a decrease of the tension across the body of the part of around 13%, and therefore there was an increase on the safety factor of around 16%. Another interesting numbers are the ones of the natural frequencies that can be observed here. It's important to say that once again there was no change on the behavior of the parts for each of the 6 first modes, and on the right it's possible once again to see the graphical comparison for the 6 first modes. Finally, it's possible to compare the results of a non-optimized, a topology optimized, and a lattice optimized part. It's interesting to notice that the lattice optimization had a higher decrease of mass, with almost 30% less mass than the non-optimized design, while it was 4% less than the topology optimized design. Another interesting factor was that the lattice optimization had smaller von Mises stresses, and consequently a higher safety factor. When compared to the topology, the lattice optimization design had higher values of natural frequencies for almost all of the modes, with the exception of the second one. And as seen before, they have the same kind of behavior, and the changes in directions here are merely due to the timing where the picture was taken. And finally, there is a graphical comparison between all 3 designs from the 6 first modes. To conclude, after this work, it was noticeable that there was an increase in the structural efficiency of the aircraft. It was possible to reach a mass reduction of up to 31%. And also, there was an increase on the maximal displacement of the parts. However, this result was not considered for the final design of the part. It was also proven that the lattice design was 4% lighter than the topology design for the same boundary conditions on the specific case. And there was also a small increment of the natural frequencies when comparing the lattices to the topology results. It's also interesting to notice that the modal behavior from both designs, lattice and topology, remain the same as the non-optimized part, and also that the lattice obtain smaller stresses when comparing to non-optimized and also the topology optimized part. Therefore, the lattice design obtain a higher safety factor when comparing from the 3 main designs obtained. Also, it's important to notice that lattice are usually harder to manufacture, and for this reason, topology optimization are usually already enough for our design purposes. Thank you for your attention. If you ever need to reach me or Guilherme, you can find us at our email. We'll be happy to answer you. And if you have any questions now, you can also do it. I will try my best to answer you.